Great. Welcome to our next session. So I'd like to introduce Kes Ward. He's a mathematics PhD student looking at anomaly detection in real-time data streams, currently based at Lancaster University. And this is about anomaly detection at the edge. Reminds me of some movies I've seen recently. Everything's on the edge. So on that note, Kes, I'll just hand over to you. Thank you very much.
Thank you very much. So my talk is about anomaly detection at the edge and scanning signals when your computational budget is low. So this is both the cutting edge of maths research, but also mainly about edge analytics and the Internet of Things. I work with the Story Center for Doctoral Training at Lancaster University, and Trevor Brelovich, who was the previous talker, is one of my supervisors for this project, which is funded by the Engineering and Physical Sciences Research Council and also by BT. So what do we mean by at the edge? So here's a very nice, good, non-sensitive application for this method. So if you have a satellite and you're hunting for flashes of light very far away in space, some of them are quite close by, and some of them are quite bright, and some of them are very far away, and they're very hard to pick out from your background rate. So your background rate is photons arriving at your satellite. And I want to draw your attention to this graph, which is just giving you a good idea of the scale of each little count here is a number of photons arriving in 1/100th of a second. And so here we have a bright gamma ray burst. So you can see it quite easily picks out as an anomaly, but finding the dim ones is a lot harder, especially because heat doesn't dissipate very well in space. So you can think a parallel to this would be an Internet Things thing. You need to keep the battery charge low. You need to keep your computational power very, very low on a very, very high velocity signal. So estimating the background is generally fairly easy to do. But the problem you have when detecting your anomalies is that anomalies could be of all shapes and sizes. We don't know how long a gamma ray burst would be until we've found it. So we need to check a lot of things on a very high velocity signal. This is a problem. So first of all, how do you check a signal? I'm going to keep the maths in this talk very, very light. So I apologize. This is the only thing of maths here. If we know the expected number of photons at a given time bin, and we know the actual number of photons, we can plug this into a calculator and we can construct like a surprise statistic, which is like, how surprised are we that this is the case? And we can correspond this to the notion of like 3 sigma, 5 sigma significance levels. So for example, if we're comparing for a 5 sigma event, so that's about 1 in 3.5 million occurred by chance, we'd want to compare to a threshold of 12.5. And there's a graph on that later in the talk. But we want to test time intervals, not just time points. But that's fine, because all of our time points are time intervals. We're looking at photons in a little interval, but photons in a bigger interval that's a collection of little intervals is still an interval. So you can just add up the expected counts and add up the actual counts and do the same maths. But the problem we get when scanning over intervals is that if we already have t points in our signal, and we add a new point to the end of our signal, we've created t+1 new intervals. This is horrifying if we are working at this kind of edge analytic speed, because we can't check these intervals. They will slow down. Our algorithm will slow down as our signal goes into the infinite horizon. So we have to do something about this. And what people usually do are one of the first 2 methods on this slide, and I'll explain the third method, which is my maths research. So the first method is exhaustive search. We say, for example, a gamma ray burst isn't going to take more than 10 minutes. So we're going to check every interval that is of 10 minutes or less in duration. Now, this is a lot of intervals, but at least it doesn't slow down as we go into infinity. This is not great for this application, though. So what people usually do for these kinds of things is we pick a set of windows. We say, okay, we're going to check 50 milliseconds, we're going to check 100 milliseconds, we're going to check 1 second, we're going to check 5 seconds, whatever. We pick a spread of windows and we only check intervals of those sizes. And all of the others, we'll just assume that it's kind of picked up where we would it'll be picked up well enough by a window length, probably. My method that I'm going to be talking about is, instead of doing that, you pick a set of start points. So you say, at this point in time, we think that an anomaly has possibly begun. So we will check every interval starting at that time point until we're pretty sure that the anomaly didn't begin at that time point, and then we'll throw it away. So just brief overview of why window methods are problems. So the blue line on this represents our sort of surprise statistic in terms of our expected and our actual count. What significance level are we at here? If something is above the blue line, we should be trying to detect it. But unfortunately, if you run a window over the data, you can only get things in the orange zone. So if you would run a load of different windows over the data, you can have a load of overlapping orange zones. That's fine. But the more windows you put in, obviously, the more computation you have to do. And then you end up with some horrific load of parameter choices for your algorithm for how many windows are we going to get and where are we going to put them. That makes just it an awful lot more frustrating from a practitioner's point of view. So what I'm looking at developing instead is working with start points. And I'm going to keep it very, very light here. And the only thing you need to take away from this slide is that some intervals overlap with each other. And if we test one interval and we know that another interval overlaps with it, it might be possible that we don't have to test the second interval because we know that an anomaly isn't going to be there. The rest of this slide I'll go into more detail, but so the way the mathematical algorithm pruning I'm working on looks is that if you have a set of start points, you have a T1 and a T2, and you think that this bit here is pretty likely to maybe be an anomaly, and then you have this bit here is pretty unlikely to be an anomaly, then at some point you will decide that for any future T in the future, you think, in fact, you know that if this bit, so if the T2 will be here, then the T1 interval here will be more surprising. And then at this point, you can throw out T2 as a start point, and you can just work with T1. So this you also, so this happens really very, very, very often when there aren't anomalies present in a signal. And in fact, you can throw out the whole interval T1 without any interval before it if you know that there is absolutely no chance of an anomaly being there. For example, if this interval contains fewer photon counts than you would expect, then you know that there is no excess of photon count. So all of this happens really, really nicely. And just quickly go through the algorithm. So on the right, you have the first 50 points here are just normal. And then the second 50 points, I've put in a little bit of an anomaly excess of count. And it's taken until time point 67 to find it at the given 5 sigma significance level. And what it's done, so at time 67 on the left, we have a collection of possible start points. And these collection possible start points have surprise curves, which are multicolored. And each surprise curve, the very top of it, corresponds to that surprise statistic I told you about before. So we have the 12.5 threshold line for a 5 sigmoid event. And we can see that the t equals 50 surprise curve has met that threshold at time 67. And we think, yep, we've found our anomaly. So you can see that, for example, all of the start points, apart from t equals 12, and that's really small down here, have all been thrown away for the non-anomalous data, which means that this works really, really quickly on a normal signal, which is great because it means we can scan all of our window lengths while not actually having to scan them. I have a variety of other algorithmic tricks, which I can't cover in this talk, that make the cost of each time step iteration really, really, really small. And we can scan for all shapes and sizes without using computational power. So we can hunt for star flashes like this, and it's also very useful on any kind of Internet of Things sensor method where we have a limited battery that we're trying not to drain, and we're trying to find anomalies immediately, and we really need both of those points. All right, it's the end of my talk. I'll probably be taking questions in the chat if it's possible.
Great, Kez. Thank you very much, and thank you for almost getting us back on time, give or take a minute or two, because we have some other speakers waiting in the panel. So if you want to ask any questions of Kez, please drop them down into the chat, because he's agreed to go online and actually answer those questions for you at the end of the day. So another really fascinating area around anomaly detection, particularly out at the edge of your systems or your network. So I'm going to bring this session to a close, and then I'll see you over on the next session in a few moments, where we have Fazil Nazir and Subhash Talluri from Amazon talking to us about how data science basically works in Amazon. I'm going to see you there in a minute. Thank you.